Hello and welcome to this design practice 2 module 25. This module is on sensors and actuators, some real case studies, and this is reflecting some research which has been carried out in our laboratory related to two different topics. One is gas sensing, where we have been enabled to use nanostructures and we have selectively etched nanostructures in a manner so that they can be selective to a certain gas, and the response, the change which is there on adsorbance of this gas on the surface of the nanostructure is merely a resistive change, and this resistance would vary as a function of the concentration, etc. So, in the second module we are showing a slightly different aspect of colorimetric sensing, where we are talking about paper flows or paper microfluidic flows through which there is the yes no answer given on the presence or absence of an analyte in a particular sample through a change in color. So, let us look at these modules. So, in module 1 we are talking about a nanoporous material, and what a nanoporous material really means, that it refers to materials having diameters between pores with diameters between 1 and 100 nanometers. So, otherwise the other portions are solid, as can be seen in the black region here, and these small closed structures here are closed pores, whereas this right here is an open pore. And as the name defines, the open pore basically is a connection of such small pores across the bulk of the volume, so that there is one continuity of a bigger pore which is there, and individual pores are the small nanopores which are there in a particular volume. So, depending on the porosity level, the number of pores per unit volume can be calculated by looking at the fraction of the pore volume to the total volume. So, if there is certain total volume of material and volume of pores which are there in the material, porosity is basically a ratio between the two. And we have the properties. There are some very distinct properties of the nanoporous materials. One is of course the high surface to volume ratio, an excellent mechanical properties, fluid permeability. So, whenever we talk about gases and gas sensing, question of gas like diffusivity comes into the material. So, a highly nanoporous material with open structures or closed structures of pores would actually lead to permeabilizing different gases through these, and so the proper desorption absorption kinetics can happen, which makes the sensor rather very quick. There is high adsorption capacity and good stability and durability in use of these nanomaterials. So, this is how the nanoporous materials are. Particularly, we would like to also delve into why nanopores for gas sensing, and if you can look at gas sensing in totality, it is a surface phenomena, and because of the porosity and the high surface to volume ratio, the quick diffusivity of gases would enable it to dissolve quickly across the whole bulk of the structure because of the highly porous structure. And so, obviously, the answer to the question of what better or how better the sensor performance would lie on what is the level of porosity of such materials. So, typically we are allowing for a case where more gas atoms can interact with the sensing surface per unit time, and these are some things which can be miniaturized very rapidly, because we are talking about very small nano level porous materials on films which are probably several 100 to 200 nanometers thick. So, we can really make a very small sensing element do a wonderful job in terms of change in resistivity, which could give you an idea of how much gas is present in the atmosphere. Being miniaturized in nature and very small volumes, you can couple them to portable devices, and it would lead to less volume consumption of the analyte which is in air. In this case, the analyte probably is a fixed gas like hydrogen, for example, which is present otherwise in not so much abundance, and because of the small size, the relative exposure to the smaller nature or smaller presence of hydrogen would be more in comparison to what would have been in case of a bulk film, a larger film. And so, quick changes in resistance could be because of the size comparison between the element and the smaller trace of the gas which is in question. And so, because of these small volumes and small sizes, obviously these are low power devices, the requirements are very small, and we can see what are the strategies which are being utilized for doing fabrication. So, in the first strategy, we have developed a highly nanoporous palladium film, and this paper was also published some time back in Sensor Letters, where we showed a very substantially high repeatability as well as very low sensing and baselining time for the particular sensing element. So, the way we fabricate is based on a step by step procedure where we are cleaning a substrate primarily made of silicon, which we clean with organic and oil, clean off the organic and the oil residue which is deposited on the substrate, and we use it or we clean it through solvents which are acetone, methanol and DI mixtures. And of course, acetone alone would leave their own residue. So, therefore, a combination of methanol and DI is used to clean the solvent off the surface, and it is completely dried up so that there is no organics. And then what we do is we actually use a process of deposition called sputtering, which I think I have discussed in some of the module earlier. And so, before this sputtering, we try to also passivate the surface, okay, by hydrogen passivation techniques, where we dip the surface in a 1:10 HF solution, okay, and then we place the passivated surface on. So, there are a lot of hydroxyl groups now on the surface, okay, of the silicon, and we place this in a sputtering chamber. So, in this particular module, what we are doing is using titanium as an adhesion material. So, once the passivated surface with, let us say, OH groups on the surface are taken to a sputtering chamber, they are first coated with a material which would act as an adhesion promoter. In this particular case, it is titanium. There is a 5 nanometer titanium which is deposited through sputter coating process. I think I have explained about. So, sputter coating is some sort of a vaporization process where there is a metal target and there is a plasma which is generated. So, the plasma knocks off some of the metals and carries the metals towards the bias that the plasma system has, and typically the substrates are on the ground plate, where this bias voltage would drive then the plasma which is there along with the material which is there to the surface. And this material is highly unreactive because it may be an argon plasma or a nitrogen plasma, where there is no possibility, and the material that we are using is palladium or titanium, where there is no possibility of generating a third species which has reacted or there are chemical bonds. So, it is taken back into the system and deposited. 5 nanometer layer is followed by again another layer of 20 nanometers, and this is pure palladium, which is actually the sensing element. We all know that palladium resistively changes because of the formation of palladium hydride at the grain boundaries, and also a change in the state change from the alpha to the beta state of the palladium. And essentially after this 25 nanometers of film, so with the hydrogen passivation, the next step is a titanium layer, 5 nanometers layer, okay, and then we are following this with another stack of a slightly thicker material, 20 nanometer palladium layer. So, this is titanium, this is palladium coated on the top of the titanium, and then finally we deposit an alloy, and this alloy is a palladium aluminum alloy which is co-sputtered from 2 targets, with one where we are using the magnetron gun, and other which is with a DC bias. So, basically both the palladium and the aluminum are knocked off together with the common plasma that is being created, and this palladium aluminum composition is deposited according to the general formula AlX PD1 minus X, where X is varied between 0.5 to 0.8. Therefore, there are cases where exactly aluminum is 50% and palladium is 50%. There are cases again where aluminum is higher, 80%, and palladium is 20%. And we deposit this in an increment of about 0.1 or 10% increment, and the total thickness of the palladium films that are being deposited in this manner is about 500 nanometers. And why we are depositing it, that because we want to make a chemistry through which we can selectively de-alloy the aluminum part, and wherever the aluminum is deposited with the palladium over the palladium bed, the aluminum comes off, and in its place there are air pores which are generated, because obviously air enters when aluminum is etched off. And so, we are de-alloying the aluminum from the surface through selective etching using a mixture of phosphoric acid, acetic acid, nitric acid, and water. And what happens is that there is a relatively high porosity level which is established by pulling out the aluminum in this manner from the surface, okay, and this constitution of the particular etchant solution to only dissolve the aluminum is 80% by volume of phosphoric acid, 5% nitric acid, 5% again by volume of acetic acid, and about 10% of DI water. So, this makes this makes it 100% ensured that we are removing only aluminum and aluminum oxide, of course. So, there is a reaction between H3PO4 and aluminum oxide, where aluminum phosphate is formulated, okay, and this aluminum phosphate, as you can see here, is solubilized. So, it comes back into the solution. So, wherever there is a presence of aluminum or aluminum oxide, there is a formulation of the +3 state because of electron transfer chemistry which is generated through the etchant. Okay. So, the etchant must have an ability to dissolve both, and so nitric acid is responsible for oxidation of aluminum. There is some oxide which is already present, as I told you, Al2O3, because of passivation of the surface, but there is some oxide which is also being made through reaction with nitric acid, and phosphoric acid and alumina kind of reacts with each other. Acetic acid slows down the oxidation of the nitric acid. So, if this step is slowed down and not much aluminum oxide is formed, phosphoric acid will actually not be able to dissolve so much alumina. So, we can have a good control by varying these percentage volumes of the various blocking agents as well as the enabling agents, so that at a certain rate etching can happen, and we want a slow oxidation process to be enabled, so that there is a porosity distribution within the whole volume of the co-alloyed material which is being deposited. So, we have now investigated the structures through scanning electron micrography, and you can find out this is pre-etched structure at magnification 50,000, and this is a post-etched structure, and you can see a lot of pores suddenly appear where the aluminum was placed. So, it is a highly nanoporous structure. Each of these pores, the scale being about 300 nanometers, indicates these pores may be about close to 20 to 30 nanometers in size, well distributed within the material, and this is also shown up in this energy dispersive X-ray spectroscopy, where in the previous prior etching or prior to etching step, there is a huge presence of aluminum which goes away, and there is a presence of only palladium which comes out. Aluminum is gone completely because of the etching action after the etching. So, this is before etching, and thus XRD shown later on is after etching. So, we are kind of sure that chemically aluminum is removed and there is porosity through the images. So, it is the aluminum really which is getting removed. So, that is conclusive out of these two experiments. Now, we want to test these small platforms which we have developed, these small films, for their various sensibilities related to the presence of hydrogen. Hydrogen is otherwise a reducing gas, so it will enable some hydride states and try to change the resistance of the material, and we can see what is the difference if it is a continuous material as opposed to the porous material that we have developed. So, for that we have a platform here which does gas sensing inside a vacuum chamber, which has a heating stage. Remember, all these elements are highly sensitive at a higher temperature. That is the biggest problem with gas sensing, that particularly semiconductor metal oxides or even metals, they cannot sense so well as room temperature as they can sense at slightly elevated 190 degrees, for example, or 180 degrees temperature. In the present case, it will be about 180-85 degrees, at which sensibility will be the highest in this particular case. So, there is also going to be a air inlet outlet where there is a evacuation step followed by a carrier gas, which would be otherwise an inert gas, in which we can selectively engage or inject through very precise mass flow controllers ppm levels of hydrogen, and then as the concentration in the chamber varies and we allow some diffusion time to happen, we exactly observe the response behavior of this element based on such changes. Okay. So, there are certain, so typically what we do is we make a set of interdigitated electrodes, okay, on a chip scale. So, the electrodes mean they are like capacitive kind of structures. I am just drawing this for an easy understanding of people. Okay. So, this is one set, the other set that can be there is going to be inside this, particular module. So, let me just do it in a little more precise manner, so that there is understanding. Okay. So, this is one set and the other set is here. So, these are like interdigitated capacitor plates which are parallel. Okay. And if I put this layer of electrodes through some sensing metals and put some contact points across which we can sense the resistivity. Typically, if there is nothing interconnecting, there is no issue, but if there is a layer of a sensing element which is interconnecting, this will actually feel the necessary resistive behavior of the sensing element, because that is the only interconnecting element between the different electrodes that is in question. So, these two posts, which are the contact posts, are used through these electrical contacts given here to sense the resistance of the resistive layer and the changes in resistance therein as we are introducing a different percentage of hydrogen gas. So, on one hand we are heating up this particular chip, this chip, and on another hand we are using interdigitated electrodes to sense what is the resistance of this particular number. So, these are some results which I would like to discuss, and these are published results. So, you could refer to the detailed paper as well later, but as you look at it, that if I had different ppms of hydrogen being sensed in, and this is a plot between percentage change of resistance of the film and the time, you can see that as the hydrogen is introduced in the chamber from 0 concentration to some different concentration here, there is an increase in the resistance, and then there is a plateauing effect, meaning that hydrogen is no further diffusing into the element, it is stabilized in terms of its environment, and then it actually falls down as the hydrogen is switched off and the carrier gas comes and occupies the place of hydrogen. Okay. So, this way we have done various plots for different ppms of hydrogen. We have also tried to see the percentage sensitivity, that is the percentage change in resistance per unit the original resistance, and we found out that the percentage sensitivity is probably the highest at about 180 degrees Celsius. So, this is the operation temperature. Okay. So, the sensor performance shows about 80% change in the resistivity with respect to the initial resistance at 180 degrees Celsius. Okay. And so, therefore, this is the operational temperature for the device. So, any device which will be taking this thin film element has to have the ability to go up to 180 degrees Celsius for absorbing the film or absorbing the gas, so that there is a change in the sensor. There is a 600 ppm H2 concentration for which highest sensitivity is again recorded, and a cycle time of 28 seconds is recorded. These are plots which indicate what happens at different temperatures. Okay, you can see that as we are making the MFC which injects hydrogen on and off, the resistance increases first, plateaus, and then goes down. And so, all these different plots suggest that around 180 degrees, which is this particular module here, the change is maximum. And the other issue that we can see is also that the recovery also, because of the highly porous nature, is more or less baselining to the same level as the hydrogen is switched off, although there is some time cycle involved in the desorption process, so that hydrides can convert back into near pure palladium, where the resistance would again be back to the baseline resistance value. These are some plots which are being plotted with the aspect of maximum sensitivity recorded, as well as the response, okay, and the recovery times. And recovery is basically meaning thereby the time that is needed for the baselining effect to happen, the resistance come back to normal resistance. And so, as a percentage of what is the sensitivity per unit, the recovery and response time, we find out that the best example can be set up through this 180 degrees Celsius, where the time scales are relatively limited. It gives a 12-second response time and a 21-second recovery time, and the sensitivity per unit, the total time that is needed for a single cycle, is also reasonably high, not high as what you can see in 220, but again in terms of operability, 180 degrees Celsius is a much better temperature to attain than 220 degrees Celsius. A lot more power will be needed in 220 degrees Celsius temperature, and maintaining it at that particular value. Okay, so that is how we can and also we see that the percentage response okay, is highest at this particular value. So, 180 degree has 80.7% sensitivity. So, therefore, from a measurement point of view, the instrumentation would behave well corresponding to this particular temperature, 180 degrees Celsius. So, this was a work which was done some time back in our group for a sensor, and you can get an idea of how you design and how you develop sensors on a practical basis. We have also investigated the sensor for the selectivity towards H2. Okay, so let us say there is an ambience created through two different gases, H2 and CO2, and we see that if we induce both the gases at 600 ppm, what is going to be the effect? So, we can see that the percentage change in the resistivity due to hydrogen is 87%, whereas that due to CO2 is only 10%. So, if there is an environment where you have equal ppm of H2 and CO2, H2 is going to be the dominant cause provider for resistance to be varying and resistance to go up to that particular level, okay, and CO2 may not be that specifically being able to get identified. So, once you prepare a sensing film, it is important to see that in mixed gases, which set of gases cause the maximum response and who are the interfering gases which may be able to deliver a similar kind of response where there may be confusion, okay, and false positives. So, this screening off is needed when you develop such a sensor element. Again, another plot at 300 ppm, you can see that 81% is the sensitivity of H2 and CO2 is only about 7%. This is reflected through the the sensitivity plots as a function of time, okay. And so, therefore, in this particular time window, it may be possible that CO2 does not give many impact at all. What this 10% number and this 7% number is based on the whole span of the time window, whereas the time scales are completely different. In case of CO2 sensitivity, it takes quite a while for the film to change in resistance, whereas H2 is almost immediate effect. So, that also helps you determine what is more sensitive and what is less sensitive to a certain specific gas. So, in conclusion to this set of experiments, what I would say is that the co-sputtering followed by selective chemical etching is what produces highly porous palladium films, and we have seen the operational performance of nanoporous palladium to be highest at 180 degrees Celsius. We also saw that sensitivity increases with increase in hydrogen ppm concentration, and the film is highly selective to hydrogen gas for sensing. There is a quick response and recovery time, and in general, you have designed a thin film resistance based sensor for sensing hydrogen. So, I am going to close on this particular module here. In the next module, maybe I will keep a small section. In the interest of time, I have to do this on the microfluidics oriented diagnostics, okay, maybe some 7-8 slides initially, before we start a completely new topic, which is about rapid prototyping and how you can handle CNC systems, etc. So, with this, I would like to close this particular module. Thank you very much.